Today we're going to talk about gas laws, actually final and initial gas laws, and how to make them very easy. First of all, we need to know all the variables that are involved in gas laws. First, we have pressure, which will be capital P. It's in units of ATM, millimeter mercury, torr, and kilopascals, kPa. These units all measure how often and how hard a gas particle collides with the sides of the container. Here's how all of them are related. 1 ATM, which is the standard that the scientists set up, is equal to 760 millimeters mercury, which is equal to 760 torr, which is equal to 101.3 kPa. For the initial final gas laws, though, we actually don't need to convert the units for pressure as long as both pressure 1 and the final pressure are the same units. Temperature is, of course, measured with a thermometer in Celsius, and we had to convert it to Kelvin. Every gas law, you must use Kelvin's temperature. So every time you have to change Celsius to Kelvin by adding 273. The other variables we need is volume, which we usually measure in milliliters or liters, so how much space the gas takes up. And then finally moles, which I know seems a little weird, but it has unit of N, because small m is used for meters, so N is used for moles. It's convert grams to moles using molar mass if we have to. So the only units we'll get here are either grams or moles. Okay, so we have several gas laws. The first one is Boyle's law, which is how pressure and volume are related. So pressure is pressure 1 times volume 1 is equal to pressure 2 times volume 2. So P1 V1 equals P2 V2. As pressure increases, volume decreases, so they're inversely proportional. Charles' law relates volume and temperature. Volume 1 over temperature 1, of course, which will be in Kelvin, is equal to volume 2 over temperature 2. And this is directly proportional. As volume goes up, temperature goes up. Gay-Lussac's law involves pressure and temperature. Pressure 1 over temperature 1 equals pressure 2 over temperature 2. Again, temperatures must be measured in Kelvin, and as we increase the temperature, the pressure of the gas will also increase. Avogadro's law has to do with volume and moles. So V1 over N1 equals V2 over N2. If we put more moles of gas into a balloon, the volume of the balloon will increase. Okay, the combined gas law actually combines Boyle's law, Charles' law. Boyle's law and Gay-Lussac's law really is just P1 over V1. P1 times V1 over T1 equals P2 V2 over temperature 2. We use combined gas law when all three of those variables are given in our problem and changing. Now, of course, one would be like the initial in a problem. They'll say like the gas was at 10 degrees and 450 milliliters. And the volume changed to 200 milliliters. What's the final temperature? So the ones with the 2 are our final ending product. In these type of gas laws, they will always give initial and a final state. That's when we know to use these gas laws instead of the ideal gas law, which we'll talk about later. Now, I like to make up a combination of all of these. Rather than trying to remember all of these gas laws, we can put them all into one and then just cancel out what we don't need. So the one I use is pressure 1 times volume 1 over N1 times T1, even though N's not used too often, is equal to pressure 2 times volume 2 over N2 times temperature 2. So this is really just combining the combined gas law and the Avogadro's law. We have all 4 variables in there then, and we can just cancel out the ones that are not involved in a problem, and we always have whatever law we need. You won't have to memorize the names of these laws, so it's best just to have how are all 4 units related. Let's work a problem. A sample of carbon dioxide gas is placed in a 125 milliliter flask. So you have to know what the milliliters is by the unit of, is it pressure, volume, temperature, or amount of gas? And of course, milliliters is a volume, so this is our V1. So the 125 milliliter flask, which has a pressure of 67.5 5 millimeters of mercury. So they told this to us was the first pressure. What pressure? So our second pressure is a question mark. How much is it? When it will be transferred to 500 milliliters. So this is volume 2. At the same temperature. So they mentioned temperature, but since they said it's the same, it's held constant, which means we don't have to worry about it. Now, what units exactly do we have? We have pressure 1, which is equal to 67.5 millimeters of mercury. We have volume 1, which is equal to 125 milliliters. Pressure 2 is a question mark. We don't know what it is. And volume 2 is 500 milliliters. Now we take our one equation, P1V1 over T1N1 equals P2V2 over T2N2. And we're going to cancel out all of the variables that are not over here listed in our given and needed stuff. So temperature and moles are not needed. So now we just have P1V1 equals P2V2. We're going to fill those numbers in. 67.5 times 125 equals P2 times 500. All right, then we are going to solve for P2, so we're going to divide by this 500. So we're going to take 67.5 times 125 divided by 500 and get that pressure 2 is equal to 16.875. And we need to look at sig figs. This is 500 points, so they all have 3. So our final answer is 16.9. Now, what unit do we use? Well, since this is pressure, we're going to look at what unit was used in the first pressure, and that will be our unit for this pressure. So pressure 2 is equal to 16.9 millimeters of mercury. For example, a mother bought a bouquet of balloons for her daughter for a birthday party. Each balloon had a pressure of 1 atm. And in the store when it was 25 degrees. So 1 atm, we need to know that atm is a pressure, and we have a temperature of 25 degrees. After buying the balloons, the mother took them to her car, and it was only 2 degrees Celsius. So it was mighty cold outside, but this was our second temperature. What would the pressure be? So we want to know what is the pressure. So here are our variables again. We have pressure 1, which equals 1 atm. We have temperature 1, which is 25 degrees, but remember temperatures always must be changed to Kelvin, so we're going to add 273 to that. And that's our Kelvin temperature. We have pressure 2 we're trying to find, and we have temperature 2, which again we need to add 273 to get 275 Kelvin. Now we take our equation, P1V1 over N1T1 equals P2V2 over N2T2. And we're going to cross out everything that's not used. So we're going to cross out volume and moles because those are not mentioned in our problem. And then we're going to take the pressure of 1 over the original temperature, 298. Equals pressure 2, which we don't know, over the second temperature, 275. We're going to cross multiply 100 times 275 equals 298 times P. And then we're going to divide by 298 to get the pressure equal to 0.923 with 3 sig figs again. And now again, what is our unit? We look at our first pressure, ATM, so ATM is our unit for this one. So pressure 2 is equal to 0.923 ATM. And this one was using what would have been called Gay-Lussac's law, but again, we don't have to worry about that because we're just going to cross out the units not used. Okay, another example. A 0.25 liter can of deodorant starts at 25 degrees and 1.2 ATM. So we have 0.25 liters, okay, so that's a volume, and 25 degrees, a temperature. and a pressure. Then the temperature is raised to 100 degrees, so I have a temperature 2, and the volume of the container does not change. If the volume does not change, we do not need to include it, so we're not going to include this volume in our calculations. And then what is the new pressure would be our second pressure. So once again, we have pressure and temperature. So we have pressure 1, which equals 1.2 atm. We have temperature 1, which is 25 degrees, which we have to add 273 to. And we have pressure 2 we're trying to find. And we have temperature 2, which is 100. Again, we had to add 273 to that. We have our overall equation here. We're going to cancel out volume and moles just like last time because we have pressure and temperature once again. So we're going to put pressure 1 over temperature 1, remembering to put it in Kelvin. And then pressure 2 we're trying to find over temperature 2. We're going to cross multiply 1.2 times 373, which will give us 447.6 is equal to 298 times P. Divide by 298 to solve for P. P2 is equal to 1.50, looking at the pressure units, atm. All right, problem. This time let's solve for something other than pressure. So we have a 15-liter container, so this would be a volume 1 at 4.8 atm, pressure 1, and 25 degrees. So here again, this time we have 3 variables. It's heated to 75 degrees, temperature 2, and compressed to 17 atm. 17 atm, atm is a pressure unit, so that must be a pressure. What's the new volume? So this time we actually have 3 variables we had to look at because nothing was said, it was held constant. So V1 is 15 liters. We have P1, which is 4.8 atm. We have temperature 1, which was 25 degrees. Once again, we're going to add 273 to it because temperature must always be in Kelvin. We have volume 2, which is our question mark. We don't know what it is. We have pressure 2, which is 17 atm. And it has a temperature 2, which is 75 degrees, which we need to add 273 to get 348 Kelvin. So here we take our equation, P1V1 over N1T1 equals P2V2 over N2T2. And the only variable not used this time is moles. So we're going to cross out the N's. When we're going to take pressure 1, 4.8. We're going to multiply it by volume 1, 15 liters, and take it over temperature 1, 298. Equals pressure 2, 17, times volume 2, we don't know, over second temperature, 348. Okay, sometimes students find this one a little bit more difficult to solve, but what we're going to do is just again cross multiply. Okay, so we're going to take this times the 348, so we're going to multiply all 3 together. So in my calculator, I'm going to say 4.8 times 15 times 348, and that comes out to be 25,056 equals, cross multiply the other way, 298 times 17, which is 5,066 times V2. We're going to divide by the 5,066 to solve for V, and V2 is equal to 4.945, but this time we need to look. We only need 2 sig figs, so it's going to be round to 4.9. What's going to be our unit for volume? Well, let's go up and look at volume 1. Volume 1 was in liters, so this one's going to be in liters. So volume 2 is equal to 4.9 liters. Okay, I hope this helps. Use an equation P1V1 over N1T1 equals P2V2 over N2T2 allows you just to manipulate all the variables very easily, and you just have to cancel out the ones that say they're constant or the ones not mentioned in the problem.